Now I start to talk about dot products of two vector and how we can use them in our 3D calculation. So the dot product if you have two vectors a and b, a and b with angle theta, and it's going to be xa ya and yb, ya and y and sorry za, that's going to be x, y and z in b, so xb, yb and zb. The dot product of a dot product of b is magnitude of the a, magnitude of b, cosine the angle between two vectors. This is how we define the dot product. Another way that we can define the dot product is that dot product of b is going to be xa, xb plus ya, yb plus za, zb. So that's the dot product as well. So you can use it either to find it from this equation or this equation. And remember, the dot product is the scalar, so it's not the vector. So the dot product of vector is a scalar. One method that we use it, we probably use it not in this method, the other way, we rearrange it. One way that we rearrange it and we use it, we use the dot product to find theta, the angle between two vectors. So theta is cosine inverse of dot product of a and b divided by a b. So it's a dot product. So to find the angle between two vectors, we calculate the cosine inverse of their dot product divided by their magnitude, and we use it. Another way that we use the dot product is when we want to calculate the projection. And how we do that is assume that we have a line AB, and we want to have the line AB. So it's going like that. So it's A and B. And then we have a vector F that has an angle theta with line AB, and we want to find the projection of that F on line AB. So we know that for the projection we always just go like that. We put the right angle here, and then the projection on AB is, at least its magnitude. The magnitude of projection on AB is the F cosine theta. So the magnitude of F times cosine theta. So it's the projection on the AB. Now if I open this one, if I write it here, so F A B, the magnitude of AB is the magnitude of F times cosine theta. So I can write it F, the magnitude of F, times 1 times cosine theta. And 1, so this is the magnitude of F, and 1 is the magnitude of the unit vector. So if I define a unit vector UAB here, the unit vector, I can rewrite that FAB is so if I define that, so if you look at that, that's the magnitude of the first vector, that's the magnitude of the second vector, and that's the angle between the first vector and the second vector. And look at here, so it's basically is the dot product of F with UAB. So if I want to find the projection of vector on a line, I dot product that vector with the unit vector of that line. This dot product gives the magnitude of that vector on that line. And that's how we are going to use that. One thing I want to mention is that make sure that you don't mistake the projection with the component. So let me give you an example of that. If we have two axes, assume I have the two axes u and v, and then I have force F, and I want to find its component. To find the component, what we used to do is that we go parallel to each of the axes. So we go parallel to axis and say, okay, this is F u, and then parallel to this axis, we say this is FV. And this is what we have here. We know that this is a component, and we know that the F is FU plus FV. But when it comes to the projection, it's a little bit different. So I draw that U and V again. So that's U, and that's V, and it's the force F. This time I want to show you how we do the projection. For the projection, we go from the tip and we draw the right angle line. So instead of going parallel, we go to have a right angle line. So it has a right angle and has a right angle. And then we said, okay, this is the F projected on U, and this is the F projected on V. So if you look at them, they are quite different. The only condition that the projection and the component are the same is that U and V has a right angle. So if the U and V are perpendicular to each other, then the component and the projection become the same. Otherwise not. And remember, the dot product gives us the projection, not the component. Gives us projection. Now that we show that we can use the dot product to find the projection on one axis, I want to show you how you can find the projection in the perpendicular axis. So again, consider that line AB that we had here. So it's line AB, and then we have the vector F and angle theta, and we show that the projection on that, the projection here is F, the magnitude of that projection is F, and then the UAB, the unit vector along AB. And let's put it this way, AB. And if this is our unit vector here, we have the unit vector UAB. Now, what if we want to find the projection on this one? Assume that we bring it here and want to find the projection of, so if we call this one projection of F on AB, call this one projection of F on AB perpendicular. How we can find that? It's very simple. If you look at that, we can write the F is equal to FAB plus FAB in the perpendicular one. So FAB, the perpendicular one, is just F minus FAB, and then you can do the calculation from here to get the FAB perpendicular to that line. So this is the projection on the line, and this is the projection on the perpendicular line. Now let's look at the example and see how we can use a dot product to find the force or vector along a line we want. So let's have our coordinate system x, y, z, and assume that we have 4, 2, 4, so it's 4, 2, and 4, and we have point here, and we have the element going from origin to that point, and so here is 0, 0, 0 is the origin, and here we have the point A, which is sitting at 4, which is sitting at 2, 4, and 4. And then from that element, from that member, we have the force apply on that vertically. A vertical force apply on that, and it is 100 Newton. And we want to find that force, the projection of that force along OA and perpendicular to OA. So what's going to be this projection? Assume that we have two axes here. We call this U and V. And the projection of the V is here and is here. So it's going to be this right. So it's going to be FU and FV. So we want to find FU and FV. So we know that F is going right upward. To do that, so like what we have before, we need to find the unit vector. If we want to find the vector along the line, or we want to find the projection, we need to find the unit vector, and for the unit vector we need to have the position vector. So the position vector here is ROA. So it's going from ROA. To find the ROA, the ROA is just is A minus A minus A minus O x component. So it's going to be 2 minus 0 I, 4 minus 0 J, and 4 minus 0 K, which is, by simplified, it's going to be 2I plus 4J plus 4K. So that's how it's going to be. And its magnitude is the square root of 2 squared plus 4 squared plus 4 squared, which is going to be 6. That's the position vector. So it's the position vector, and it's its magnitude that we have. And from there we can calculate the unit vector on the OA, which is going to be 2 over 6, which is going to be, or put it there, is a ROA divided by its magnitude, which is going to be 2 over 6 I plus 4 over 6 J plus 4 over 6 K. So that's the unit vector along that we have. And if you look at the force itself, the F, if I look at the F itself, the F is going upward. It doesn't have the X component, it doesn't have Y component. Also, only it has the component on the Z axis. So the F itself I will write it here. So the F itself is 100 and K. It only has the K component. So it has a K component. Now we want to find F on the U axis. The magnitude of F on the U axis is the dot product of F and UOA. So the dot product of F, the vector F, and gives us that. And we know that the F is 100K, and the dot product with 2/6I plus 4/6J plus 4/6K. And then we know that the I component times together, J component times together, K component times together, and then add them together. So what we have here, the magnitude of FU is going to be, so the I component here is 0 times 2/6 plus, again the J component is 0 times 4/6, and the K component is 100 times 4/6, which gives us 66.67. So that's the magnitude of F along the OA axis that we can use. Now let's look at the now we want to find the vector of Fu. The vector of Fu is its magnitude times the unit vector. So this here is magnitude dot product of F and unit vector, but here its vector is its magnitude times the unit vector, and its magnitude is 66.67 times the unit vector, which is going to be 26I plus 4/6J plus 4/6K, which gonna gives us 20.20I plus 44.44J plus 44.44K. So that's the vector that we have. Now if we want to find the FV, we know that if I write it, that you know that F is FU plus FV. Therefore FV is just F minus F U, just in the vector form. So FV is F, which is 100K, minus FU, which is 20.20I plus 44.44J plus 44.44K. And then, so it's going to be 20.20I minus 44.44J and plus 55.56K. And its magnitude, if you want the magnitude, so it's the FV, and if you want this magnitude, it's going to be 20.20 squared plus 44.44 squared plus 55.56 square root of that, which gives us 74.53 Newton. So its vector, it's magnitude, and it shows us how we can use the dot product to find the magnitude of vector, how to use the unit vector to find its vector, and then the vector perpendicular to that, so their projection on the u and v axis.